So again, thank you everybody. Simplify Power AC/DC coupling, NABCEP credited event. To get the credit, you got to stay until the end of the course, and we'll show you an email address to request the NABCEP credits. Without further ado, Simplify Power has been around since 2010, albeit under a slightly different name. We were founded under Optimized Energy Storage and Liberty Pack, doing energy storage for the film and video industry. Some cool things that happened there. I don't know if you saw Tron, where they had the light up suits. Those were using our battery technology. In 2011, 2012, we started Diversify, finding a need in the military where forward operating bases were using generators with heat signatures and flooded lead acid batteries that were arriving with issues, either unresponsive or problematic batteries, and they wanted something different. So they looked at lithium ion and found that a problematic history made them not want to adopt that technology, and we were able to convince them that our technology is different due to the chemistry. It's safer. It doesn't have the thermal runaway issues that some other lithium iron phosphate batteries have. And they gave us an opportunity to deploy our batteries, and they were successful. Our batteries were deployed at forward operating bases around the globe, and some are still in use today. In 2013-14, we started to diversify the product line even more, concentrating on like that cabinet you see there that would become an iteration when we launched Simplify Power in 2015, 2016 of one of our cabinets. So we have several cabinets. We'll go over them later in the presentation, but in this image here, you have an access cabinet or a Boss 12 cabinet where you've got an outdoor rated cabinet with batteries or batteries and an inverter. 2017 to 2022, we started ramping up production, more different product lines, including a high voltage product line. And then most recently, due to the acquisition of Simplify Power by Briggs & Stratton, we have leveraged their manufacturing capabilities to produce a vertically integrated energy storage system, or ESS. So this is a battery, this is an inverter, and a monitoring system, all in one. Super exciting for a battery company to come out with an inverter and monitoring capabilities, all under one brand, one warranty, one tech support call. We'll go over these products in detail later on in the presentation, but this is really what we're talking about today. When we've got energy storage systems, we're going to be AC or DC coupling an energy source or a power source to those energy storage systems to charge the batteries. Well, why are we doing that? Well, we've got problems. We are seeing in California here, for example, escalating energy costs. It's out of control. We're seeing rate increases coming out 2, maybe 3 times a year. We're not alone. We're seeing those rate increases around the globe. Generating power is becoming more expensive. Some of this is generated by, global events. There's wars that will cause shortages in oil. Those drive up the price. So there's a lot of uncertainty around the costs of energy. People are taking that into their own hands. We also have infrastructure problems. At the top of the presentation, Nathan, who's here presenting with me today, asked about the weather. And if we had power, we do, thankfully. But several areas in California today are experiencing heavy rains, landslides, power outages. And that's not the worst of it. We see California shutting off its grid just because it's hot and windy and dangerous. So the utilities will turn off the power because they don't want to start a fire. We've also seen it recently in states like Texas, where increased usage during heavy weather events is causing the grid to fail. And overall, our infrastructure is aging. So a lot of problems related to the grid. And another problem is the global warming problem. So a solution could be decarbonization, where we start to produce less CO2 into the atmosphere, trying to take climate control into our own hands. A lot of us in the industry are very passionate about this aspect. We all want to keep the lights on, that's great. We all want to save money, that's great. But when we have the opportunity to save the world, that's amazing. And so solar, wind, hydropower are clean, renewable energy resources. And by taking those resources into your own hands and using energy storage, you can be part of the solution. So we have several solutions, like I talked about in that timeline slide. All of them are going to come with three primary themes. They're safe. We use a non-toxic, non-hazardous battery chemistry. It is free from cobalt. That differentiates us from many lithium-ion products on the market. We actually have an entire hour-long presentation about battery chemistry, if you want to check it out, where we go into in-depth what that means. What does it mean when we have no risk of thermal runaway with fire propagation? Spoiler alert, it's good. You do not want thermal runaway with fire propagation. It's not good. Because of these safety factors, we are certified, UL certified 1642, which is the cell of a battery, 1973, which would be the battery itself in the cube, and 9548, which is a system level test that informs a 9540 certification. Also, due to our safety, we are able to do some things that other lithium-ion products cannot do. UN DOT certifications allow us to air transport our product. They don't want a product going on a plane unless it's safe. Another certification we have is SGIP. Again, that's a rebate program here in California where you can get money from the utility to help purchase your battery. So not only are we safe, we're proven. We've been around since 2010, like I said at the top. And with over a decade of experience, with a 10-year warranty, we have products that are in the field that have outlived their warranty. Not a lot of manufacturers can say that because a lot of lithium-ion products are relatively new to the market, 2, 4, maybe 6 years. So if they've been around that long, they've got a 10-year warranty, you know, it's not exactly proven yet. We are deployed worldwide in more than 45 countries with something to the tune of 250 megawatt hours installed. Like I said at the top, the military, US Army, and Marine Corps have used our product. And we're also trying to prove that we can demonstrate a social impact while maintaining profitability. We do this through, for example, our IDEA program, where the I in IDEA is actually a 1 for 1%, and that's 1% of our revenue that we will, or our profit that we will donate towards a project that we deem worthy. So we've got several deployments through the IDEA program to schools, parks, emergency services. If you think you have a project that may be worthy, let us know. We'd love to look at it and see if that's something where we can make an impact. Like I said about safe, the FAA lets us airship. So there's an aspect there that is proven as well. And we're manufactured in the US. It's in the name, simplify. We're simple. We integrate with just about any inverter or charge controller on the market, existing or new. And we're going to store that power for you simply so that you can access it when you want it, when you need it. This gives you the ability to maximize energy security and resilience. Like we talked about, it's stormy. It's good to have that resilience. And there's also opportunities to save money by taking those batteries, maybe when you're not due for an outage, and using them to offset your utility usage, using them to offset time of use rates or demand charges. So lots of opportunities there for cost savings as well. So here's a little bit of overview of what we're going to be talking about today. What we're talking about is charging batteries. So we're going to use a couple different terms. We're talking generally in the concept of PV, which is photovoltaic, or solar energy. That is the most commonplace use for our batteries, but our batteries could also be used in applications with wind or hydro. I have a friend up the hill who has a creek running through his property and has a hydro generation that charges his battery bank. And I'm sure it's making a lot of power right now because we got a lot of water flowing. So how do you charge those batteries? Well, there's primarily two ways. AC coupling, which takes AC power, which is alternating current. It's what we're used to seeing in our homes, powering the lights, our computers, our TVs. So we're going to take that AC power from a PV array and convert it into DC, or direct current for battery charging. All batteries are DC. And even if they say that they're an AC battery, that just means there's a DC battery down there with an inverter built in. You may be familiar with some of those. They come in a 13.5 kilowatt hour flavor. Still a DC battery, just it's got an AC inverter. That would be an example where you're AC coupling. Another option would be DC coupling, where you take DC, direct current power, and you don't change it to AC. So you're taking that DC power from the PV and you're regulating that charge to charge your battery bank. Then your battery can be converted to AC power to use it later. So we're going to go into a bunch of the details about how AC and DC coupling, or coupling could be compared to like pairing with a battery. How do you pair AC power with a battery? Well, we're going to use the word coupling, but the concept is the same. So how do you couple AC and DC power with your battery? DC coupling first. It's been around the longest. So DC power comes from the generation source to the batteries, direct. Stays DC the entire way. Now, typically this is converted using a charge controller. What a charge controller does is it says, okay, I know that my battery is, say, 48 volts, and maybe my PV array is 600 volts, and I need that 600 volts to charge my 48 volt battery. Well, if you wire it straight in there, there's going to be problems, right? So you put that charge controller there to control the charge, to regulate, not only to step down that voltage from, say, 600 to 48, but also to allow the battery to say, hey, charge controller, I think I'm full. Can you stop charging me? So your charge controller is going to take care of your battery by regulating voltage and amperage supplied to the batteries, filling them up. It's also a good way to optimize your PV source. We'll talk about a couple different ways that a charge controller can optimize solar, and they're rather different. When you're DC coupling, it's important to think about how your PV is arranged. You know, when we have shading, when we have shading on a solar panel, it's not making as much power. So now typically if I'm DC coupling, I'm putting a bunch of solar panels together in a string in series and potentially combining those strings of solar panels in parallel to my charge controller. Well, if one of those panels is shaded, it's going to take down the production of that entire string with it. Now, that's just solar panel to solar panel. We'll talk about some solutions where you can optimize DC production, but generally speaking, if you have shade, you want to be really careful about how you string your solar panels. You also want to be careful about how those strings add up. So there's some values known as VOC, or voltage open current, which is if you took a solar panel and you held the two positive and negative leads up in the air, they're open, they're not connected to anything. Put your voltmeter in there and you measure it, that's open current voltage. It's the highest possible voltage for that solar panel with no current. Conversely, there's ISC, or current, the I is for current, short circuit. Now that would be if you took your solar panel and you connected it to itself, and you put a clamp on meter on it now, you'd see a current, but no voltage, and that would be the highest possible current. There's also a voltage at maximum power and a current at maximum power. And all these values are going to be very important when you're trying to configure your system, because like in that earlier example where we say we have 600 volts, well, if I have a 50 volt panel and I put 12 of them at 600 volts, I'm great, right? Maybe not, because there will be variables in the environment that affect that voltage. For example, cold weather increases the VOC. So if I had those 50 volt panels, I put 12 of them together, I'm at 600 volts, and then it gets cold, I could be well over 600 volts and damage the equipment that I'm connecting to. So it's important to design a DC coupled system carefully. One of the ways you can take DC power from a solar array and charge your batteries is through a charge controller. Well, what does a charge controller do? Like I talked about at the top, it regulates voltage and current going into that battery bank to hit specific set points. and limitations defined by the battery for charging. So a DC charge controller could be doing solar as PV, it could be doing wind, it could be doing hydro. And there's basically two major ways that a charge controller works. One would be maximum power point tracking, and the other one would be pulse width modulation. An MPPT charge controller is generally more efficient, more expensive, but more efficient. Because an MPP charge controller is taking real-time measurements and adjusting based on what the charge controller says it needs. Tracking that production is going to increase the efficiency of your DC solar source to your DC battery. And MPPT can be very efficient. So let's look at them both. Pulse width modulation is basically taking a singular voltage, represented here in this blue bar, and pulsing it again and again and again at really, really short intervals, way faster than you and I could switch on or off a switch, many, many times per second. And because of this voltage right here, maybe it's a little bit higher than what our 48-volt battery wants to see, but because it's turning on then off, the average voltage seen by the battery is appropriate. So it's modulating these pulses. How's it doing that? It uses these little components called FETs, little switches, and then some smart electronics. Like I said, generally speaking, it's less efficient than MPPT, but it's cheaper. So it could be a really good fit for a smaller system, maybe a couple panels. Maybe you've got a remote astronomical observatory on a mountain, and you just need a couple of batteries to take care of your equipment and a couple panels. And a PMW charge controller could be a great fit for that application. On the other side is the MPPT charge controller. So what does this do? Well, we've got this graph here. On the vertical axis, we've got current with an I. On the horizontal axis, we've got voltage with a V. This red curve here, I like to call the knee. It's kind of shaped like a knee. So what an MPPT charge controller is doing is riding the knee. We talked about open circuit and short circuit. So a short circuit would be up here on the vertical axis, all of the current, none of the voltage. Voltage is at 0, highest possible current. Likewise, open circuit would be down here, highest possible voltage, lowest current. Well, if we know Ohm's law is power, watts, is equal to voltage times current, either of these times 0 is a 0, so that's no good. We want to get out here on the knee where we're getting the maximum power from that available power source. And the way we do that by riding the knee is making adjustments. So the piece of equipment may come out here and say, okay, I'm at 50 volts. And because of that, I'm getting whatever, 10 amps. This is my maximum power. This is great. But is it always my maximum power? So I'm gonna make a little adjustment. I was at 50 volts. I'm gonna go down to 49.8 volts. Did my power increase? No. Okay, back to 50. All right, let's try going the other way. Let's go to 50.2 volts. Did my power increase? Oh, yes. Okay, then let's go this way. Because of these micro adjustments in real time, the MPPT is able to maximize power in various conditions. So that may be shade, it may be, your environmental considerations like rain. It may be that your battery is saying, hey, I'm starting to top off here. I don't need as much current. And so your MPPT tracker can actually modulate how much, instead of maybe riding that maximum, that charge controller could say, okay, let's tone it down and finesse the end of the charge. So MPPT is used in tons of solar technology. It's used in a charge controller like we're talking about here, but it's also used in microinverters, string inverters, DC optimizers. It's a very common technology in solar, and it's very efficient can be up to 99% efficient. Generally speaking, an MPPT charge controller is going to be more expensive than a pulse width modulation charge controller, but that's because you're getting better power out of it. So within a DC coupled system, we've got several components. How do they all tie together? Well, over on the right here, we've got our PV. And then here we've got our charge controller. And down here, we've got our battery. And then up here, we've got our inverter connecting to the grid and our loads. Well, one thing that brings these all together is a bus bar. So this is where our DC coupled solar is going to interact with our batteries. So I'm charging my batteries. My batteries are also providing power to my inverter here, feeding my loads, potentially exporting to the grid. And in systems where your batteries fill up, you can actually have what's referred to as essentially a battery bypass feature, where the charge controller is taking the DC current right off this bus and feeding it to the inverter. Batteries say, hey, I'm full. And the solar says, I want to keep going. I want to start saving this customer on some time of use or demand charges. And now I can export to loads or the grid. So this is a very basic, diagram. You will obviously want to look at your DC design and make sure things like wire sizing, amperages are appropriate, voltages are appropriate for the equipment, and so forth. But this is kind of the concept for DC coupling. You've got a DC charge controller charging your batteries, and then an inverter that's taking DC and converting it to AC. Here's a system design example. Very simplified again, but what we got here over on the left, some solar panels. Looks like it's rooftop solar because we've got some, looks like some Tigo rapid shutdown modules. Looks like that's a Tigo rapid shutdown controller that's being controlled by this Solarc inverter. So this is a hybrid inverter. It's a concept we haven't talked about yet, but that inverter is able to take an AC source, say from the grid or a generator, and use it to charge the batteries, in which case this is a inverter charger. But it can also take a DC source from the solar or the batteries here and use that DC source, just like an inverter, to serve backup loads or export to the grid. On the bottom here, we've got two BOSS 12 cabinets. This is our Simplify cabinet with 12 batteries in it. Again, it's an outdoor rated cabinet. In the middle here, we've got a midnight combiner where we've got 24 batteries here, and we need to have them all paralleled and with equal length conductors so that they're all balanced. This allows the inverter to get that DC power out of that battery bank. I see a lot of activity in the questions and answers, so thank you, everybody. Keep those questions coming. Nathan's on it. Any questions that we don't get to in the Q&A, we will answer at the end of the presentation. Now let's talk about AC coupling, the flip side. So DC solar is how it all really started. There was DC solar, there wasn't really grid connections, everything was charging a battery, and then those inverters were serving loads. Well, along came grid connected solar. So AC power coming from an inverter. And this is how a lot of grid connected homes have standalone solar, no battery. That you maybe have a string inverter, like an SMA or a Fronius on the side of your house, where the PV from the roof is coming down in DC and being converted to AC and being used for home loads and going to the grid. Maybe you have micro inverters on the roof. All of these would be examples of AC power coming off the roof or coming from a ground mount. Micro or string inverters are all PV inverters in this language. And there are some arrangement considerations. So when I have an AC coupled system, I'm going to need to have one of these hybrid or battery based. That's what the BB here stands for, a battery based inverter. In order to have that grid tied inverter interact with my batteries, it's got to go through one of these hybrid inverters, have that inverter charger aspect to be able to feed that AC power again, from the grid, from a generator, or from an AC PV source into a DC battery. And using a generator is effectively the same thing as AC coupling. So we'll have some line diagram examples, but essentially what we do here is we take that existing grid-tied PV system, we install a hybrid inverter or battery-based inverter. Now that can feed the AC PV into it and charge the battery. How is this accomplished? Well, there's a lot of magic. There are differentiations to this. There are brands that use frequency shifting in different ways, but basically, at the most fundamental level, to be a grid-connected inverter, you have to follow certain rules. And these rules include things like, I will only operate within grid specification. Say, maybe it's, plus or minus a couple volts from 240 volts, 60 hertz. And if I don't see that, I'm a grid-tied inverter, I turn off. This is a safety feature, because if it's raining here and the power could go out, and if my PV is cooking and the power goes out and a lineman comes out to work on the pole, my PV is still cooking, I could injure that lineman. So I want that PV to turn off if it sees an unstable grid. Well, a battery-based inverter is going to take advantage of that and use frequency shifting to regulate control of grid-tied output. Essentially saying, okay, hey, grid-tied PV, you're doing great. Keep it coming, keep it coming, keep it coming. We're full. I'm going to shift my frequency. So instead of 60 hertz, in the US here, the grid is very reliably 60 hertz. The fluctuations from 60 are minimal at best. So I can shift my frequencies from 60 to, say, 60.2. And all of a sudden, my grid-tied inverter freaks out, says this grid is unstable, and shuts off. Well, that's perfect for the battery-based inverter, because it was trying to stop charging the batteries. The batteries were getting full. You can't overcharge your batteries. So frequency shifting is the most common method for controlling the charge from a PV source. The battery-based inverter shifts the frequency to reduce output or to stop output. And now the battery provides loads. And I should have prefaced this is without the grid. So when the grid goes down, the battery-based inverter is controlling the PV on the roof. So there'll be a disconnect from the grid, and you create a microgrid. And now you're controlling that PV. In grid-connected mode, that frequency is coming from the grid. And like I said, it's very, very stable. But in the event of an outage, this is how a battery-based inverter will control grid-tied PV that is AC coupled to it. There are some considerations to be made here. And like I said most grid-tied inverters will have these frequency ranges that are very specified. There may be some equipment that's either more customized. Sunny Island, for example, has a frequency shifting method that is different, where they will actually be curtailing power instead of like an on-off. And there may be some older equipment out there that doesn't respond well to the frequency shifting, doesn't see it, doesn't care, or whatever it is. And that could be bad. If your batteries are filling up in an outage and you shift frequency and that inverter doesn't turn off, now you're at risk of overcharging your batteries. So it's always good to confirm how an AC coupled project will function. And that could be as easy as reading a spec sheet or calling the manufacturer and just confirming that there is a frequency range that inverter will operate in, and that your battery-based inverter will control that. Here's a quick single line about AC coupled. This is just grid-tied PV. You got the utility, you got your main loads panel, some microinverters, look like some Enphase on the roof, a little solar combiner feeding to the grid. So this is just net metering. But you could come out to this system and sell them a battery, and that would look like this. You would drop in one of our access cabinets with a Solarc 12K, 6 batteries in, and now this Solarc 12K is able to frequency shift these microinverters out of production when the battery gets full, again, in the event of an outage. And now it can serve a backed up load center. So if you walked out to a home where there was existing microinverters on the roof and they want a battery, can they do that? Absolutely. Just picking the right equipment, making some modifications here, and maybe moving some loads to a backup load center. So how do we apply this out in the real world? So very little argument exists that in an off-grid situation, DC coupling is best. Now, the reason for this is several-fold. Batteries have a charging cycle. If you're familiar with lead acid, you were doing typically a 3-stage where you would bulk, absorb, and float. If you're doing lithium ion, you're doing something similar, but except bulk and absorb are your 2 stages, and float is kind of not really a stage. You kind of set the set point so it doesn't really float, but it does, but not really. So a DC coupled system has that finesse. It has the ability through a charge controller to handle those charging cycles. Whereas AC coupling, AC PV just does AC PV with few exceptions. It only has one speed. So it makes it difficult to charge the batteries all the way up to the top because that single speed as you get towards the top may be excessive, and you don't want that single speed of charge all the way to the top. So a DC coupled could be a backup only system. It could be an off-grid system. If you're going into power outage, like I said, you want to protect those linemen. So you're going to go into what's known as island mode, where your microgrid essentially becomes its own island. So you're not backfeeding to the grid. And you're able to charge the PV through a DC coupled method during an outage. But it's not limited to that. You could still have a DC coupled situation when a grid tied inverter or on a grid tied application where you're using it as cell for just kilowatt hour exchanges with the utilities, for time of use arbitrage, peak demand shaving, and so forth. So the big takeaway there is that, specifically off-grid DC coupled is superior because of increased efficiencies and the ability to take your batteries through those charging stages. AC coupled applications. Again, you come out to this barn, there's already a ton of AC PV, and they want batteries. Well, why do they want batteries? They probably want batteries because the grid's going out. Like I said at the top, there's problems. People are losing power. But there's other cases as well where this grid-tied situation, maybe they've been on a very favorable net metering agreement, and that net metering agreement is changing. Maybe they're taking away the export rates. Maybe they're reducing the export rates so significantly that you no longer want to export your power. So you could install a battery and you could use it, like I said, same thing on the DC coupled, you could use it for time of use, for self-consumption, or for peak demand shaving. So a lot of the same applications exist there. And we will cover where there's some discretion about, if you walk out to an existing system, does it make sense to go from AC coupled to DC coupled, or the opposite? Does it make sense to go from DC coupled to AC coupled? So we'll take a look at that. Principally, you want to look at how much work is entailed. So if I have an existing PV system in AC coupling, it could be very challenging to turn that into a DC coupled system. Essentially, I'd have to go up to the roof, maybe they're microinverters, and I'd have to rip off all the microinverters, string it, run it down to a charge controller, to a battery, and then a hybrid inverter. So a lot of work to go from an existing AC coupled system to DC coupled. But you can put in a hybrid inverter. So you don't need to do that. You could take that existing AC coupled system, whether it's a string inverter on the wall or microinverters on the roof, put in a hybrid inverter, and now you're AC coupling to your batteries. So you can go into island mode. That hybrid inverter has the ability to do that, and you get all those previously stated benefits about utility, arbitrage, shaving, and stuff. There is a bit of a misconception that you cannot do DC coupling with grid-tied systems. And that's not really true. I mean, it's derived from the fact that an existing ACP system is going to have some serious retrofitting challenges. It's not maybe just tearing off the microinverters. if I had strings of 12, 50-watt modules, right, and a 600-volt charge controller, oh, I'm set, right? We got to go back to that consideration about temperature and open circuit voltage. So you might be not only removing the AC of the PV, you might have to restring the whole thing, depending on the equipment you choose. And like I said, there is an efficiency difference. AC PV coupling will have several changes. So if you have AC PV coming off the roof, you got DC to the microinverter, it's coming down as AC. Now you're going through an inverter, hybrid inverter, converting it to DC, storing it in the batteries, and then you're calling it up for your loads later that evening. So it's going from DC to AC again. So that's 3 conversions from DC to AC in the life cycle of that energy, each time losing a certain amount of efficiency. So there's a give and a take there. The point being that you can take an existing PV system and retrofit it to be an AC coupled system, maybe losing some efficiency, but saving a ton on equipment and labor. An interesting aspect of all of this AC and DC coupling is rapid shutdown. So depending on your jurisdiction, or AHJ, authority having jurisdiction, you may be required to have rapid shutdown on buildings. Now, what rapid shutdown is trying to accomplish is safety. So in the event of a fire, it's very likely the fire department will come out to the building, and depending on their firefighting protocols, they may choose to get on the roof and start sawing into it. They may try to vent the fire out of the top of the roof. They may be doing some other firefighting techniques. What they don't want to do is encounter a PV system that is electrified. So they want that PV system to be rapidly shut down for safety. So if they get up there and start chainsawing around and accidentally hit some conduit that's running through the attic that they can't see, they don't want that to be hot. And so I believe it was NEC 2017 where the first rapid shutdown requirements came out. They've come out more and more stringent in later adoptions in 20 and 23. And so ask your AHJ about what rapid shutdown requirements you're going to have to face, and that may inform whether or not you do AC or DC coupling. But what do the two look like? So DC coupled. Talk to the AHJ, they say absolutely, you have to have rapid shutdown. You have to have it down within a certain voltage, usually a pretty low voltage, within the array in a certain period of time. Well, how do you get there? You could do module level shutdown with a DC coupled system. You could have DC optimizers where your solar panels coming into a panel level electronics on the roof, and it leaves that panel level electronics still as DC. That equipment could be doing voltage regulation. Maybe we're trying to hit a certain voltage for the inverter to be happy. Or that panel level electronics could simply be a rapid shutdown only box. Some examples of that would be, like we saw earlier, the Tigo rapid shutdown devices in that single line, or AP Smart, another rapid shutdown device we are featuring in our new Simplify energy storage system. And generally, these systems will have a single button, a red plunger button where you turn them off and by hitting the button. And so the fire department shows up, building's on fire, they hit the red button, and now they know that the roof's safe. Similarly, with AC coupled systems, how do you achieve this module level shutdown? Microinverters. It's another panel level electronic. And because your inverter's on the roof, it's still looking for that grid signal, that 240 volts, 60 hertz. And as soon as it doesn't see that, it powers down. Well, that's a great way to achieve rapid shutdown. The other way you might get around AC coupled rapid shutdown requirements is that if it's an existing installation. So if you're coming out doing a battery retrofit to somebody who's had PV for 10 years, and the PV system on the roof 100% does not have rapid shutdown because it wasn't a thing 10 years ago when they installed it, you can talk to your AHJ and say, hey, we're just doing battery here. We don't want to go up and rewire the entire roof. And they may let you do that. So you may be able to do an AC coupled string inverter with a battery-based system. You could also put in DC optimizers. So, if you had a solar edge system, you got DC optimizers on the roof, and you could be going to a hybrid inverter and charging that battery through AC coupling. Generally, there'll still be a big red button. AHJs love the big red button. But realistically, with a microinverter system or solar edge system or one of these older string inverter systems, you may only just need to turn off a breaker. Or sometimes the fire department will pull the meter, and that cuts off the grid. And all these devices are looking for that grid essentially as a keep alive signal. So there's different ways to accomplish DC and AC coupling to meet rapid shutdown requirements. Here again is a rapid shutdown example for a DC coupled system. We've got our big red button. We've also got a blade disco here, which could satisfy your AHJ. So this is why it's really important to find out what your AHJ wants. Are they on the newest NEC cycle? The bladed disconnect might not do it then. They might want to see the rapid shutdown initiated, where this red button's telling the solar to trigger this, PHI shutdown, so that it achieves a certain voltage in a certain time frame. An AC coupled example. This one does not have the red button, so maybe the AHJ said it was okay. You could come out here, you could just pull the meter, or maybe throw a breaker. There may be rules about how many hand movements it takes to de-energize a system. So again, it's worth checking. But essentially, if this Schneider inverter was keeping these N-phase microinverters alive during an outage, the breaker ought to do it, or this bladed disco, because that's going to disconnect the PV from the keep alive signal of that hybrid inverter. Now, you may also face requirements where the battery system needs to be de-energized for similar reasons. The fire department doesn't want to go in if the batteries are keeping the home powered and there's a dangerous situation. A couple of system design considerations. We talked about a little bit on the retrofit slide, but with DC coupled, since we're limiting amps through a charge controller, generally we're using pretty small strings. You might have 2 panels running to a charge controller in a string. You might have 12. But because of that difference, you may have very complex wiring runs where, that 12 panel system, if I'm running 2 panels in series, means I have 12 home runs or 6 home runs coming off the roof. That's a lot of wire. So you want to think about whether or not, if those efficiency gains or losses warrant the additional work. You're running a whole bunch of number 10 wire off the roof for that customer. Another consideration, maybe, if we're running a small off-grid system, it could, or a small system, it could be independent of the grid, or it could not. And having the grid down not be a limiting factor for your DC coupled might be where you win. Most of these systems are also going to use a critical loads panel, because what's the point of having battery backup if you don't have loads that can be powered during an outage? Similarly, on the AC coupled side, you're not limiting amps through a charge controller, you're actually limiting amps through the inverter's output. And you're going to want to read the spec sheet. That may be different than its nameplate for an off-grid setting. It may say it's a 10K inverter in grid tied, but only be a 7.6 in backup. So it's important to understand how big that inverter is, what the limiting factor to your charge is, especially in an outage, because without that grid to go to, all the power you're making is going to your batteries. So you want to look at how those limitations for grid up and grid down different when you're doing AC coupled. Generally speaking, with AC coupled, you can do larger strings, typically strings of 10, 11, 12, maybe 13, maybe higher if you're using DC optimizers. And because of this, you're doing less wiring, less home runs off the roof. And always, you're going to need a critical load panel to power loads in an outage. So how does Simplify fit into all this? Well, we've got a bunch of key features that make it really important to understand that we've got this chemistry that's safe. Because of lithium iron phosphate, we're not using cobalt. We don't have thermal runaway with fire propagation. Because of our form factor that's cylindrical, We don't have problems with expansion and contraction of the battery cells over time that may cause those battery cells to degrade faster, may cause ruptures internally. So our battery is going to be the safest chemistry and form factor on the market. This gives us, I mentioned at the top, the ability to get UL listings relatively easy. I mean, the UL process is very detailed, and that's for good reason. You want UL listings to be safe. But because our batteries are safe, we're able to go through and get certifications around fire and disaster. Like I said, 1642, 1973, and 9540 certifications. And 9540 being based on a test where they actually take cells and force them into thermal runaway. It's called 9540A testing. And what happens next informs how that 9540 certification goes. If your cells go into thermal runaway and propagate, meaning one cell starts to have thermal runaway and so does the next cell, and the next cell, and then that whole battery, and then the battery next to it, then you might have to have deflagration radiuses, you might have to have fire suppression systems. Your system could get much more complex for the AHJ to approve it. So why else would you want UL certifications? You're like, I'm not permitting it, I don't care. Well, what about insurance? What if your insurance underwriter says, we don't want that system? Or what about if you sell the house? So it's a really good idea to always seek UL certifications and make sure you're doing the best practice. So let's talk a little about our products. We've got the PHI battery. This is a 3.8 kilowatt hour. Comes in a 24 volt and 48 volt variety, 48 being the most common for AC coupling because most hybrid inverters are going to be operating in that hybrid or in that 48 volt range. It's not exclusive. You might find hybrid inverters in 24 or 400 volts, but our 48 volt battery is going to work with a ton of equipment that's already out there. So you can be doing DC coupling or AC coupling with a hybrid inverter. If you're doing a battery-based inverter for AC coupling, you got to remember that you're going to be going, you're taking an AC source in, you're putting it in the battery, and then it comes out as DC. So there's potentially some efficiency losses there from the inverter. Of course, if you're doing DC coupled, the only efficiency loss you have is that one conversion to AC. We also have our Amplify battery. Same idea as the PHI battery in form factor and cell, 3.8 kilowatt hour, 48 volt, but it has closed loop communications that will work with the Solarc or the Simplify inverter. So an Ethernet cable runs from battery to battery to battery and then up to the inverter. And this is going to give the inverter the opportunity to read state of charge very accurately. Voltages, temperature, there's temperature sensors within the battery that will tell the inverter, hey, I'm getting cold. We need to slow down my charge rate because we cannot charge lithium batteries below freezing. We have another hour-long presentation about harsh environment considerations where we talk a lot about how lithium-ion batteries in the cold or the hot have considerations that are worth knowing. So do lead-acid batteries. But because of this closed-loop communication, you auto-populate a ton of set points. I like to say you auto-populate the set points the battery wants, but that there's customer expectation set points you still need to program, like how far are you discharging your batteries, 80% or 90 or 100%, or what is other equipment doing? When's my generator kicking on? So commissioning with an Amplify battery is simpler, but there still are some set points that you should set. And we have an increased level of protection due to temperature variations. Like the battery can tell the inverter, hey, I'm cold or hot. I need to ramp down charging or discharging. We have our access cabinet. So this is an outdoor rated inverter plus batteries. It's got a maximum power point tracking options. So the Solarc has it built in. Schneider can be added on. We're coming out with one of these with our Simplify inverter as well, where MPPT is also built in. So you could use this as an AC coupled retrofit. You could go out to that house with microinverters, pour a slab, drop this on it, wire it up, and now they've got AC coupled battery backup. Beautiful. There are some sizing considerations to make sure you understand where that AC PV array, if you've got 50 kW of AC PV on the roof, you may not be able to run all of that into a single access cabinet. You may need to either add multiple cabinets to absorb all that PV or have some of it not be backed up so that we can maintain the PV to battery ratio that is safe for the batteries, which is essentially a C/2 charge rate. Gives you the ability to add critical loads. You can also add additional storage through like another box cabinet. And it's got that automatic transfer switch so that we're having that islanding effect where we're not endangering the linemen. Like I said, it's outdoor rated. It's got cooling, or it's got fans inside so you can cool the equipment, and super easy for permitting. Our Schneider and SolarArc units are already 9540 certified, and we're working on the Simplify unit. Really excited about the release of the Simplify Energy Storage System, or ESS. It is primarily 3 components: the 6 kilowatt inverter, a 4.9 kilowatt hour battery, and our energy track control and monitoring system. So the 6 kilowatt inverter has that built-in transfer switch for virtually indetectable downtime between an outage and grid tied. You have the ability to stack these inverters. So you might say, hey, Chuck, 6 kW is not enough. Great, we can stack up to 9. How does 54 kW sound? Good? Great. It's got a screen. I love the screen. I'm old school. You know, in the event of an outage, I'm probably going to lose internet too. So I don't want to rely on an app to go bounce off the cloud and come back, especially if I can't get to the internet. So having a screen is a really good feature, especially when you're looking at backup. It's commissioned through the Energy Track app, and it's outdoor rated. The 4.9 kilowatt hour battery is the same battery chemistry we've been talking about in the PHI and Amplify. It's just a bigger form factor. So the same cells, same closed loop communication that the Amplify has, it's just bigger. And 4.9 is kind of a magic number. If you're out there in one of those AHJs that doesn't want you to have more than 20 kilowatt hours of storage, go ahead and throw 4 of these, and you're at 19.6 kilowatt hours, meeting the requirement of the AHJ, but maximizing the storage that your homeowner has. 13.5 kilowatt hour chunks don't work like that. You're either 13.5 or 27. There's no way to fit under that. Also outdoor rated, also a 10-year warranty like our other batteries. Energy Track is the app. So this puts control in the installer's hand for commissioning, the homeowner's hand for monitoring, and a fleet view for the installer. So it's given a bunch of features. You can be setting set points via the app, monitoring your fleet. The homeowner can look at it during the day and figure out how much solar they're making and what their battery's doing, you know, if they know a storm's coming. We have lots of tools on the website to help. You might be going for the first time for a battery. We can help you size that. You might be doing a lead acid replacement. We can help you size for that. I should have said at the top, we will be sending out this slide deck, so you have access to all these links. If you haven't already been to our website, it's a great resource. We have manuals. Read the manual. We have spec sheets. It's very important to understand when you're designing the system. And one of the things that we have that really nobody else is doing are these integration guides where we'll say, hey, okay, you got a Magnum. Here are the Magnum set points for our battery. You got an outpack, same thing. And the integration guides are written in such a way that if you are out there programming that piece of equipment, that it'll give you the set points that you need. So check out simplifypower.com. You can go to our product documentation. If you need help, you can always give sales or tech support a call at that number, 805-640-6700. I want to talk real quickly about our IQ program. Our IQ program enables us to identify installers who have been working with our products and are qualified, and will put you on the map. So someone who's interested in Simplify can go to our website and plug in their zip code, and they can find an IQ installer that's near them. So we're actually directing leads your way. We also have a newsletter where we're featuring IQ installers. We have a photo contest where you can be submitting photos. We love photos of installs with the customer or their pets. We love all that. And we have a cash back program where you can get $25 in a rebate, cash or check, really, that we'll send you when you register the warranty on our website. So if you're an IQ installer, you're installing a ton of batteries, you can be getting cash back. If you're interested in the IQ program, you can scan that QR code. It'll take you to our site. You can fill out the application, We'll review your application. We're going to have a phone call. We're going to talk about what you've been doing. How many installs do you have? How'd they go? What your equipment? What set points were you using? And really what we're looking for there is, are you an installer that's qualified? IQ. We want to get you in your program if you are. And everybody's been waiting for this slide. I appreciate your time today. You can reach us at training@simplifypower.com to request your NABCEP credits. Be sure to tell us how you want your name to read on the certificate, because if you go by Bob, but NABCEP has you as Robert, and when you do the certificate for Bob, you might not get the credit that you want. You might have to come back and ask us to edit the certificate. So email us at training@simplifypower.com. Let us know you want a credit. Let us know how your name reads. We'll get those credits out to you before the end of the week. And if you have any questions, give us a call. Nathan, it looks like we have a couple of questions and answers you haven't already answered, and I appreciate your hard work in the background.
Yeah, so there was one asking about end-phase micros that I wasn't sure about. It said we showed a picture of those being shown with a solar and our batteries. And so it was just asking about, can we operate with the smart switch PV management system from Enphase? And I know that for older units that we can. I'm not sure if it's been tested with the IQ8s yet. And Chuck, I'm not sure if you have more information on that.
Yeah, I would ask this attendee to potentially clarify. So with the Enphase topology, there is an Enphase MID, or micro interconnection device, so you got your Enphase combiner where all your strings are being combined. Then you've got another box where those Enphase batteries are coming in. It's got its own MID. Which is the ability to disconnect from the grid. It's got its own auto former. It's got relays and all kinds of stuff. You would not want to use that piece of equipment with something else. That Enphase smart switch is an Enphase product for Enphase batteries. So I don't see that being compatible with an off-the-shelf inverter, solar or otherwise. And I'm not sure if that answers your question or not. Not hop back in the chat and let us know. But again, that microgrid interconnection device is going to be native to your hybrid inverter. But what you don't want to do is start to have all these different MID devices from different manufacturers. That could cause, I can't even imagine the problems that would cause. So, Mateo, if that's not the answer you're looking for, hop back into the chat and let us know. Robert asks, certifications are a challenge for new system design permitting. Yes, they are. What do the new solutions carry for residential grid connected PV battery backup with genset design? So I think what you're referring to there is our 9540 certification. A lot of AHJs are requiring that any energy storage system has a certification. The good news is we do. The bad news is there's probably a level of education that you may need to take your AHJ through to fully understand. So if they're blanket stating that 9540 has to go on everything, you may have to educate them that 9540 is a system level certification. So if you were piecing together, say, a Simplify battery with a different hybrid inverter that hasn't gone through that certification process, you're not going to get that certification stamp. But that's okay, because you could use our access cabinet with a solar converter and Simplify batteries and have that certification. So I definitely understand, Robert, the landscape right now is very uneven. Some AHJs aren't requiring anything. Some AHJs are requiring the moon. And, like I said, there's a little bit of education there, but there's also, understanding the products that you're offering. And hopefully you're getting that clarified before you've gone under contract with the customer, because I know how disruptive that can be when you get pushback on a permit package. Again, hopefully that answers your question. If not, hop back into the chat and ask again. Michael asks, do you have some kind of fireproof placard showing firefighters what chemistry is used, UL certification on cabinet or in battery area? I believe I know what you're referring to, Michael, and it's not something that we typically provide because it is AHJ specific. So many AHJs will require these red placards. They're like hard plastic and they're engraved, and they are pointing out some of your questions. Generally, they're not discussing chemistry, but they're discussing locations of equipment and how the firefighters will access that. So that's, you know, a placard for them to read when they arrive in an emergency. Your plan checker is probably the one that's looking at chemistry, UL certifications and such. And so, you know, that roadblock's going to happen way before installation, hopefully. And then that requirement for a placard, again, is going to be very AHJ specific. Hopefully that helps. UL 1741 SB. I don't know what the SB stands for, Robert. If you wanted to shoot us an email at training@simplifypower.com, we can ask our team. I am relatively confident in our battery chemistry that if there's a UL certification out there that we don't have, that we can get it. It'll take time for sure to run through the testing process, but I'm not exactly sure what the SB is applying to. So maybe there's some clarification there. It may be a question.
So that's an inverter. That's an inverter certification. I'm not sure what the SB is as well. So 1741, yes. What specific inverter are you looking at, Robert? And I'm not sure what the SB is either.
But yeah, we can take that one offline for sure. We may, like Nathan said, if it's an inverter question, we may not have the answer unless it's our inverter. And in which case, if you know you run into a specific installation, it may make sense to approach that inverter manufacturer.
And the last one here is Michael's. This
was a CALSA comment. One change happened right before the new year. Was not the result of a new law, but rather PG&E's bungled rollout of a new interconnection provision from the 2020 CPUC decision. Yes, you're referring to NEM 3.0, I believe, Michael. 2 weeks ago, they began asking what anti-islanding method is used. Oh no, this is something different. Used by the inverter manufacturer. This is insane that they expect contractors to know this, and held up interconnection applications over the question. CALSA did not know. And as agreed, or CALSA pushed back and PG&E has agreed, I don't know, opt.
So again, Chuck, I think we're going to have to defer to the inverter manufacturer for their anti-islanding, safety measures that are put in place. And I think it would depend on which type of inverter that you're using. So I would advise you, Michael, to contact the inverter manufacturer, whether it's Solarc or Schneider, or if it's us, contact us and we can find that information for you. And yes, a lot of the rules surrounding ESS systems seem insane.
Yeah, and again, there's a big learning curve there. Michael, feel free to email us, but like Nathan said, we may not be able to answer unless it's specific to our inverter. And an attendee has requested a recording. We will send out a recording of the presentation to all attendees later this week. And we'll also send out the slide deck. One more question. Looking at solutions. So this is the UL 1741 SB. And yeah, we'll see you at future training, Robert. Feel free to send us an email if you have any other questions. We appreciate all of your time today. Stay safe out there, everybody, and Happy New Year.